So in the Stoke F is an unramified finite extension of QP. QP, and E, which is my coefficient field, will be a finite extension of Fp containing the residue field of F. Finite extension of Fp containing Fp to the F, which is the residue field of F, where residue field of F. So in particular, F is a dimension of F over Qp. So I take rho, being a continuous representation of Galois Qp bar over F to GL2 of E. And I tried to explain yesterday that if rho is sufficiently generic so far, well, for F equals Qp, there's no need of sufficiently generic for all rho, but for F different from Qp, as far as I know, we need this thing, which I didn't make precise due to a lack of time, essentially. But for rho sufficiently generic, then one can associate in a kind of naive way to rho a big set of smooth admissible, well, of isomorphism classes of smooth admissible representation of G. G is GL2F over E. And if rho is irreducible, then this set all these representations are all irreducible. And if rho is reducible, then they're all reducible because they all contain one principal series. And so so one big question now which arises is, can we refine this set? Of course, we're not satisfied with such a thing. We would like to, ideally, we would like just one representation here, corresponding to one Galois representation, even if it's very specific. We'd be happy. So we're not happy with this, and I want in this to try to refine, to show you a way which enables you to refine a little bit this big set. But unfortunately, it will still remain big, and I don't know how to refine more. But okay, so yeah, something I forgot to say, that I need an assumption to do this. I need, moreover, that rho is semi-simple. Otherwise, I don't know how to refine. If rho is semi-simple, so irreducible or split, and being also sufficiently generic, the aim in the Stoke is to try to refine, well, it's not try, we're going to refine this set.
Sorry, did you tell us yesterday was sufficiently generic?
No, I didn't. It's a little bit technical to, this is, it's not that hard. It's, if you take a random row, it will be like this, okay? You have to avoid the things like trivial representation, for instance, or the extension of 1 by omega exactly, and so on. You have to avoid these things. Well, presumably you can do things, sorry?
It's a purely numerical condition.
Yes, it's a purely numerical condition.
Or at least we don't know whether there is a...
Well, it's what makes the combinatorics of these weights of Buzzard-Diamond-Jarvis work well. If you are not generic, then the combinatorics kind of a little bit collapses. You have to, you have less weights. It's a kind of a, okay. It's much easier. And if you don't assume generic and F is not QP, it is again, much more complicated. I don't know what to do. And even for generic, there's so many questions. Okay, so anyway, this refinement will use phi gamma modules. So let me very quickly recall phi gamma modules in the setting. I guess most of you know what this is, but so phi gamma modules were introduced by Fontaine some time ago. And in the setting of the Stoke, a phi gamma module will be the following. So a phi gamma module over E will be by definition the data of a finite dimensional E double bracket X vector space. I consider the most down-to-earth definition. I go right to the point. Okay. So it's a finite dimensional E double bracket vector space together with, so let me call it M, together with an E-linear action of gamma, which is the group obtained by joining all p roots of 1 to qp, so which is isomorphic, as you know, to zp cross, such that, so it is E-linear, but it is semi-linear with respect to the action on x. So you have the usual action such that if A belongs to zp cross, I will denote by gamma sub A, the corresponding element in the Galois group. So gamma sub A of xi dot m is 1 plus x to the A minus 1 to the I gamma sub A of m. So it's usual semi-linear action on x. So you expand this, the usual formula, which was written on the blackboard before. And that's one thing. But the most important thing, in some sense, is not this action. The most important thing, as it turns out to be, is a Frobenius. And E-linear endomorphism phi going from M to M, commuting with gamma, with the action of gamma, and such that, well, it's again semi-linear with respect to the, it's E-linear, but semi-linear with in x. So phi of applied to xi dot m is x to the pi dot phi of m. Okay, so this is a general phi gamma module, and a phi gamma module is said to be étal. Phi gamma module over E is said to be étal if phi of m generates m over E of x, which is equivalent, which turns out to be equivalent to the following thing. You have an isomorphism like this. So m twisted by E of x, but here you put the Frobenius, and here you put the map identity tensor phi, or phi, and this is isomorphic to m. So this is it turns out to be equivalent to this. This is not better formulation in some sense. Okay, so, well, phi gamma modules form a category in an obvious sense. Maps are E of x linear maps commuting with phi and gamma, and you've got the subcategory of étal phi gamma modules. I mean, you can define morphisms, okay, in an obvious way. And the main result, which holds in a more general setting, not just in characteristic P, of course, but here I am in characteristic P, and this makes things much simpler, many places. So the main result, which is due to Fontaine, which is at least 20 years old, even more now, which is there is an equivalence of categories between étal phi gamma modules over E and continuous representations of Galois of QP bar over QP, not F, otherwise you would have to modify a little bit, QP bar over QP over finite dimensional E vector spaces. Continuous linear, E-linear representation of Galois QP bar over QP over finite dimensional E vector spaces, and of course this equivalence preserves dimension on both sides. The dimension of the phi gamma module over E of x equals the dimension of the Galois representation over E, of course, as you know. This is, well, I don't need to make you, to tell you exactly, to make you precise this equivalence. I'm not really going to need it, since I'm only going to remain in the world of phi gamma modules. So you need to know that there is a, well, which is a strong motivation, of course, that there is a Galois representation corresponding to it. But somehow I don't need to tell you the equivalent. I mean, it's not that hard, but Okay, that's all I need for phi gamma modules. Now let's go back to GL2. And first I will assume GL2 QP. I will assume F to be QP. So this is 2. Now here I assume FQP. And I'll take a row which is a continuous two-dimensional representation of Galois QP bar by QP, GL2E. And although for QP it's not necessary, but still I'm going to use it after, I will assume it is semi-simple. But here this is you can dispense on this. I mean, but it's convenient for me for the rest of the talk. So as I told you yesterday, and I even gave you or at least gave you some information about the representation. To rho, you can associate a representation pi, which is a GL2QP smooth admissible representation over E. And I told you what it was yesterday, more or less. So in the case it is irreducible, this is this compact induction mod T, and in the case rho is a split, this is a direct sum of two principal series. Okay? Then there's, it turns out one can recover from the phi gamma module of rho, of the dual of rho, to be precise, from pi. And this was found by Kolmez. And here's the recipe. So.
Continuity assumption, definition of phi gamma module.
You mean, yeah, okay. You mean, yeah, I mean, okay. You mean to extend it to all power series in X or something like this, or?
Yeah.
Yeah, yeah, you're right. Okay, so if you take a power series in X, you apply this to. I mean,
M is a vector space over this.
Yeah, a finite dimension.
Complete
Yeah.
field, so it has a topology, and the gamma action has to be continuous in this topology. No?
Well, but doesn't it just mean that? Let me see. It means that
The same topology
it's finite dimensional. also.
EX to
Yeah.
the D. Yeah.
No, each single operator is continuous, but I mean the gamma action has to be continuous.
Ah, okay. Yeah, probably. Yeah, you're right.
Typically forgotten by your people. That
Yeah. Okay. But I mean, this is anyway. It turns out that as you will see in this talk, the main point is not the gamma action,
Yeah,
which is
sure.
kind of always there and doesn't is the main point is the Frobenius.
Yes.
That's the main point. Well, that's the condition of etalness, and so on. So no, okay. So you're right. Continuous. All right. No, yeah, I kind of. I mean, gamma is a topological group. Okay, so you have to take this into account. You're right. Continuous, an linear continuous action. But I'm not going to speak a lot about gamma in this talk anyway. To keep the Frobenius, rather. Okay, so let me give you how you can recover M. Well, first, you can define the following vector space. So you take. So I take a kind of down-to-earth definition, once again, going to be as concrete as possible. So you consider the following E sub-vector space of the dual of pi. No, sorry. Well, to be a quotient, since I dualize. Anyway, you consider the sum from n equals 0 to infinity of Pn Zp01 applied to the socle of pi. I could, with my assumption of semi-simple, this will be enough. So remember, the socle is, in that case, is the direct sum of two Serre weights. Okay. So I apply this, which for all n, I take the sum of this inside pi. Okay, and I take the algebraic dual, the dual. Okay, no condition of smoothness or whatever. This is the dual as an E vector space, and this thing is naturally a module of a the Iwasawa algebra of 1 Zp01, because 1 Zp01 preserves the space in an obvious way, and I tensor by the fraction field of this. So which I will just write a double bracket x, where x will be well, the usual thing. I mean, in terms of the IHES algebra, it is 1, 1, 0, 1, class of this minus the class of identity, 0, 0, 1. As usual, okay? And well, there's an action of gamma on this, continuous, because it just comes from the fact that, so the action of gamma is the action of ZP cross 0, 0, 1. And this comes from the fact that ZP cross 0, 0, 1 preserves the space, because this is a K representation. Okay, so it preserves the space. So there's no problem with the gamma action. But now there's an action of, now I have to define a Frobenius, and this, so this is there's a subtle point, although I'm just going to point out to you the subtle point, since although it's a subtle point, it won't be what I'm going to do in this talk. But still, I want to. So basically, the Frobenius is the action. So phi is basically, or comes basically from the action of P001 on the dual, meaning it is the action of P minus 1, 0, 0, 1 on the vector space itself. Since, of course, when I dualize, I want to keep the left action, in sense. But the point is that P minus 1, 0, 0, 1 doesn't preserve this vector space, n equals 0 to infinity, Pn Zp 0, 1 applied to the soc k of pi. Because obviously you may have denominators when you apply P minus 1, 0, 0, 1 here on the left, you may at some point find denominators here in the entry, and this doesn't preserve this space. So you have to define phi a little bit differently. So okay, so let's so this matrix doesn't preserve the space, but if I take P, it does. Okay, obviously. So this does preserve this vector space. Okay, and it induces the action of induces. So the action of P001 induces a map as follows. So this is again naturally a module of the IHES algebra of 1 ZP01. I mean this is smooth, so ZP01, and so it induces such a map. So let me call this W. Sorry, for notation is not terrific. It induces such a map where here you have the map where x maps to x to the p. So this is the action of P001. So this is well, just see how it acts on ZP, and this is trivial, basically. The fact that this is semilinear in that sense is completely trivial. So you have this. Now you take the dualize. You dualize this, and you get a map from W dual to W dual tensor. Well, you have to do the same thing. E1ZP01, E double bracket 1 ZP01, and here the map is again x maps to x to the p. Okay, and then this is where you have to prove something. And then we can prove that if you invert x, this map turns out to be an isomorphism, but you have to invert x on the right-hand side. So this is a fact. I mean, it's not so hard. It's just you can compute everything on these representation pi, because it's the most nice case is the case of a n sigma mod t of a supersingular representation, but you can compute everything since the equation t equals 0 is a kind of easy equation. And this is the problem, that we don't have such easy equations when f is not qp. Anyway, the fact is that this is an isomorphism, becomes an isomorphism after tensoring by E of x on the right-hand side. And you define phi to be the inverse of this isomorphism. So you have to do this. And so you see, you exactly find that phi is an isomorphism from A of x, tensor A of x. Well, you know, am to m, with here your Frobenius. This is exactly what, this is an isomorphism, of course, what we have in the definition. Okay, and the main result of Kolmez is that this phi gamma module, so m, this m, is exactly, so coming from the representation pi, only coming from GL to QP, is exactly the phi gamma module of the dual of rho, well, which is just rho up to twist, since we're with GL2, but. Okay, now what ultimately we'd like to do in a way or another is to generalize this to GL2F. So now.
Oh, excuse me.
Yes?
So I can understand where we're going. Isn't it correct that, I mean, isn't what we want to do is to get pi from m rather than m from pi?
Well, we can do both.
But isn't this what actually I'm just trying to?
No, but you see, in my
m is already defined.
in my case, I have too many pi. So, well, yes, I mean, I could, yeah, you're right. I mean, but to get rho from pi, I don't know. To get pi from rho, there's also a recipe, but I mean, you see in some sense, this, I really don't know anything about this.
I understand, but getting m from rho is a recipe that you understand in general.
M from pi, you mean?
No, m from rho. That's what I'm saying. Getting from the Galois representation to the phi gamma.
Ah, yeah.
I know that in general.
Yeah. No,
so
this is easy.
Isn't it more intuitive? I thought what you wanted to do was to get the pi from m, and
yeah, you can also do this. But what I'm telling you is that this is something that I'm going to work out in the non-QP case right afterwards. Whereas the thing you're mentioning, I have no idea what to do when f is not QP at all. I mean, you can get pi from m, okay?
in this case,
in for QP.
Right.
But this, I have no idea how to get a full GL2F representation, even of infinite length or whatever, when f is not QP from a
I
row.
understand. So what I was thinking is that isn't but still the motivation. I thought you wanted to understand this process of getting pi from m well enough to generalize to f, but that's not what you're doing.
My aim is to refine.
Right.
My ultimate aim is to refine my set of pi, and I'm just.
I mean, are you doing something like, I mean, you know how to get m from rho, and you know how to get m from pi, and you can narrow down the class of pi by saying it's the same or something like that? I mean,
So maybe first you should forget about rho, or you should identify m and rho. I mean,
Yeah,
this is something which is entirely on the Galois side. Forget about it. So this is m and pi. Okay. So you have rho, which is the same thing as m. So you can get pi from m and m from pi. What I'm explaining here is how to get m from pi.
Right.
Okay, because this is the thing I'm going to use.
right.
This
to
is
narrow it
what
down.
you generalize it.
Yeah. Well, except okay. Let me go on now. Is it okay? Okay. Okay, so this is so we ideally one of the things we like to do is to generalize this, and with other things as you mentioned, but also this. Somehow this is a simpler direction. You know, this is a simple construction. I mean, this is completely explicit. You get explicit your phi gamma modules. It's transparent. So you hope to generalize this. So let me now start from rho, which I will assume semi-simple. And again, I need this assumption that I didn't make clear to you, if you being sufficiently generic. And with f being different from QP and ramified. And then I take one of the pi, take one of yesterday's pi. And so you can do something, obviously, well, you can do several things, but here's one natural thing you can do. You consider the sum from n equals 0 to infinity of p to the n of 0, 1. You apply this to the circle of pi, viewed as a k representation. K is GL to OF. Yes, well, okay, this is yesterday's notation. Yeah, you take the algebraic, so this exists inside pi. You take the algebraic dual, and so you see this as, again, a module over the Iwasawa algebra of 1 OF 0, 1, okay, which is a power series ring in several variables instead of just one variable as previously. And there you have two possibilities of what you want to do. So you can either tensor this by a big field. So I guess this is what Peter Schneider and Vinieras are doing. Or so I don't know if you're taking the fraction field or a suitable localization of this. I think it's a suitable localization, right? It's not naively the fraction field. You still have a kind of trace map to
we only work over QP, right? I mean, our point is going to more general groups.
Oh, I see.
But the principle is the same.
Okay. Well, this is not what I'm going to do. This is something very interesting to do, but this is not here. I'm going to do here something much more naive. For the following reason is that I'm going just to take the trace.
No, but I mean, this is exactly enough.
Oh, this is what you're doing exactly?
No, I mean, don't take the trace, but you go with a functional, you go down to one variable again.
Oh, I see. Okay. Okay. So I take the trace from F to QP, so I get a map from the Iwasawa algebra to the Iwasawa algebra in just one variable, and then I invert X. So, here's one thing we would like to compute, okay, among other things. Okay, but the point is, the problem, as far as I know, no one knows how to prove that this is of finite dimension. It is not known. One doesn't know if this is finite dimensional. And the very reason why we don't know this is because we don't have explicit equations for the pi. So we're stuck in some sense so far. And for QP, it's not difficult to prove it's finite dimensional because you have an explicit equation. But since you don't have explicit equations, I mean, you don't even know whether there's a finite number of equations as a quotient of compact induction of sigma to define such a pi being admissible and so on as in the theorem with the right circle. So we're stuck. So what I'm going to do is something else, something more naive, which...
non-zero.
Sorry?
You know it's non-zero.
Yeah, okay, it's non-zero. Yeah, I know it's non-zero. I mean, I rather want to prove it's small rather than big, but it's non-zero, yeah.
But so what good would this do? Because you'd get a Galois representation of QP bar over QP, not
Yeah. Yeah, but I don't know how to, yeah, okay, if I do this, I get if this turns out to be finite dimensional, I get a phi gamma modulus, which is a representation of Galois QP bar over QP, yes, but this is still something, I don't know how to get a representation of Galois QP bar over F from this, using phi gamma module construction.
Which one
Yeah, I mean,
maybe the question is, which one should it be?
yeah, or which one should it be? Okay, my aim is to refine my set, and this is a way to refine it, and this is a kind of natural thing to do. Okay, but of course it's QP. But you're going to see it's. I don't know if this is what I'm going to speak about, but maybe it is. So, but I'm going to do something else now. Okay. So since I don't know whether this is a finite dimension anyway, I forget about that from now on. I just wanted to explain to you the natural sequence of events somehow. Okay, so from now on I'll adopt a much more naive point of view. There's a posteriori, there is a more naive way. So a posteriori, there is a more naive way to get m from pi for f equals qp. And this is this way, which is kind of a recipe. You can generalize it and make computations for any f unramified. That's what I'm going to do. But I need some preliminaries for this. Yeah, let me just state as a remark about this is that this Iwasawa algebra has several variables. So this is not, I mean, the phi gamma module of the theory of phi gamma modules of Fontaine over F still has one variable, because this is a local field, okay, one-dimensional local field. So you, even if it's not QP, so I mean, you see, to get anyway, I mean, you're not happy with Galois QP bar over QP. You want Galois QP bar over F, but somehow I don't know what to do. Whereas if you take the trace from F to QP, at least you, well, okay.
Sorry,
That's the usual problem with this stuff.
you don't. I guess you say you don't want to talk about this, but
No,
if,
yeah,
if there,
anymore.
but if you wanted, if there were a desired representation of QP bar over F, what would be the relation with this representation?
Well, you'll see.
Okay.
Maybe. I don't know how to compute this once again, but maybe the relation is what I'm going to write down. Okay, so I first need some preliminaries. Okay, so let me make a certain number of considerations from group theory. So I have my circle of pi. Well, let me just say that this again, as Peter was saying, this is, you kind of go back to QP. So this is, again, not so kind of natural. That thing, in fact, if you go down to Q, this is where things will, well, you will have maybe generalization of these things. Anyway, so let me take such a pi and let me compute the I1 invariant. I remind you that the I1 invariant is the Propi. So of course the soc of pi is a direct sum for sigma in the set of cell weights defined by Buzzard, Diamond, and Jarvis of sigma I1. Okay, and each of these, as I told you, is one dimensional over E. Okay, it's irreducible. Okay, so this is something. Sorry?
Just two of them.
No. I'm with F. Ah, okay. So this is okay. So the yeah, but this will hold for any F. You're right, but okay. For any F, you have this. So it's the dimension is exactly dimension is exactly 2 to the F. Remember from yesterday. Okay, that's one thing. And the second thing, which is a result from group theory, nice result from group theory, which is, I mean, kind of elementary. It's nothing mysterious, but which is a nice result. So you can prove that, one can prove that if you take a non-zero vector, a non-zero basis in one of these vector space, in sigma I of 1 for one of these sigma, then there exists, so let me write this. Then there exists a unique integer s of sigma, which is between 0 and p to the f minus 1, such that if I define S of v to be the sum for lambda in f b to the f of lambda to the s of sigma p lambda 0 1 applied to v, this is in v, in a pipe, and this is the Teichmüller. Then this is non-zero. Is non-zero and is still I1 invariant. So let me rephrase this. I start from an element in the circle which is invariant under I1, and well, which is in more precisely, which is in a sigma I1 for one of the sigma. Then I claim that there's a unique integer s of sigma, such that when you consider this formula applied to V inside pi, then you get something which is both non-zero and again I1 invariant. If you take any S sigma, you may get something non-zero, but it will not be I1 invariant. Okay? So here, exaggerating a little bit, this S sigma depends on an embedding of my residue field inside E, because here, lambda here is in the residue field of F. But here I put it as a coefficient, and this is where I use that the fact that my field E contains the residue field. So S of sigma actually depends on this embedding, up to, up to Frobeniuses and so on. But what I'm going to do with it after the rest of the talk won't depend on it. I'm only going to use the digit in base P of S of sigma anyway. So if you multiply S of sigma by P or things like that, you don't change the digits in base P. Okay, so this was just a remark in case you wonder what is this. I have to choose here an embedding of my residue field inside E, but what I'm going to do won't depend on this S sigma. So
But why don't you just take the type moment?
oh, but here I mean characteristics, well, I mean,
You followed by the projection.
yeah,
Yeah.
you still have the same problem that you need, so this lambda is in the residue field of F on the,
Right.
and I put it as a coefficient in E. So I need to choose the embedding of my residue field inside E. There's no way I can avoid this. But it won't depend on this, what I'm going to do. S of sigma does, but
Still have
what I'm going to do with it won't.
realize in some ring of the vectors, you still have to embed, then choose an isomorphism between this field.
Okay. So you have so this is certain property, and the final thing you can check that this S of V, which is again the I1 invariant, is actually the I1 invariant of another weight. Actually, S of V belongs to delta of sigma I1 for another for some delta of sigma again in this set of weights. I mean, it could be, it could be the sum of I1 of vectors which have components in many weights. No, it's just again concentrated as the I1 invariant of one weight. So you have, so this gives you one map. This gives you one permutation on these weights, which is this map delta. I mean, okay, don't know it's a permutation, but one can prove, and this is not difficult, that this map S induces an E linear isomorphism from soc k of pi I1 to soc k of pi I1, and that delta induces a permutation on this finite set of Buzard-Diamond-Jarvis weights, D of rho. For instance, if you take if you are with QP, and if you take the direct sum of two principal series, then delta is the identity. It's just perhaps one way to another way. And if you take irreducible Galois representation, so you have two weights here, then delta is just the permutation on these two weights, sends one way to the other for QP. It's more complicated when you have F different from QP, but you can work this out completely, and this, I'm going to do this in a minute. And let me just say that S and delta don't depend on anything. In particular, any choice of embedding don't depend on any choice. Okay, so what do I say that to you because I want to give you now a posteriori recipe to recover M from pi, which is not functorial, so it's a kind of an ersatz. It's a bad replacement of something nice, something not so nice, but for which at least you can compute a bit. So a posteriori for F equals QP, so if F equals QP, one can also recover M for rho semi-simple by the following recipe. So as a vector space, as an E of x, E double bracket x vector space, M is just E of x, tensor over E, the I1 invariant of the circle, which I dualize. Well, there's a dual also. This is a finite dimensional E vector space. I just take its dual, and I tensor naively by E of x. And this is a dimension 2. Because remember, there were 2 weights in the case f equals qp, and rho semi-simple. And that's for M, and for phi, which is the main point. What is phi on this M? So then writing soc k of phi I1 dual to be direct sum for sigma in the not of rho of sigma I1 dual. I can one has for f in sigma I1 dual. I only need to define phi for these elements here, since by linearity I extend it to all of them. So phi of one tensor f, this belongs to my M by definition, one tensor f, is the following. This is S of sigma factorial. So I am with f equals qp here. S of sigma factorial x p minus 1 minus s of sigma tensor f composed with this map s minus 1. Yeah, so it looks a little bit more less transparent, and it is in fact, but this is what you have. So once again, this map for a principal series, it's just essentially the identity on the 2 weights, and for a supersingular, it's just permutation on the 2 weights. And you have a power of x, which is made out of this S of sigma that I described. So here there's no problem of embedding because I am with f equals qp, so fp embeds canonically into E. So I don't have so S of sigma is well defined for qp. Okay, so when f is different from qp, I just keep the same recipe.
Gamma action?
Sorry. Ah, yeah. No. Okay. So there's no. The gamma action goes on. I mean, there's no. You have to work out a bit, but the gamma action is no problem. You're right. The gamma action. So let me. I say something. Yes, the gamma action comes from the action of zp cross 0, 0, 1. So except that if you just apply this action of zp cross 0, 0, 1 here, it doesn't necessarily commute with phi, but there's a canonical way to make it commute with phi. So this, I mean, I don't want to insist on this because really this is not a problem. It is there and satisfies all the property you want. The main point is the Frobenius.
I'm sorry, this coefficient factorial here was the number up there, lambda to the S sigma.
Yeah, it is a number between 0 and p minus 1.
The
Yes.
unique number.
Yes. So I take, I see it in z mod pz inside E. Okay, so for f different from qp, if f different from qp, just define M by the same recipe. So, but let me make it, there's still one point where you have to be careful. So M is exactly the same. So now I raise f equals qp.
Sorry, I get,
Yes.
yes, it's the one. But this gamma action, so that preserves this soft I1 invariant?
Yeah, of course. This is an action of I. So I1, I normalizes I1.
Oh, yeah, I see. Okay.
So it preserves the
Sorry,
I1, of
alright.
course. It doesn't commute with phi but there's a canonical way to make it commute with phi, just by adding powers of x in a canonical way. and you recover the phi gamma module of your Galois representation, the dual of rho. Okay, maybe I should, now I don't speak of gamma anymore, because that's not the point somehow. This is no problem with gamma. The important thing is the Frobenius. Let me insist on this. So I want to, for any f unramified, so I don't recover anything since I don't know how to, but I define phi gamma modulo by taking exactly the same, and I have to, and I write the dual of I1 invariant as like this. I take f here, and I just have to make clear what I mean here, because of course now s of sigma is an integer between 0 and p to the f minus 1, and obviously this can be 0, and I don't want 0. So I just take the product of the, let me write what I say, what I do. I take s0 factorial, s1 factorial, s f minus 1 factorial, then x p minus 1 minus s naught, x p minus 1 minus s1, that x p minus 1 minus s f minus 1, where s of sigma is the sum from I equals 0 to f minus 1 of si p to the I, with si being in 0 p minus 1. So I take the digits in base p of s of sigma, and you see if I change my embedding, I will change the order of the digits, but I won't change the product, neither here, neither here.
Yeah, I didn't understand this. What is S sigma?
S of sigma is this S of
That's the
sigma.
digits of
It
the
is the
order.
thing that starting from an element v in sigma I1 makes you another one.
Right,
by
but now
this.
you use, or you write it in, okay. This-
Yeah. This is the other way. I should.
Sorry, the x's here? What?
X to the p minus 1 minus s naught times x to the p minus 1 minus s1. I take the product of these. Yeah. This is a definition. I mean, no, I mean, this is not completely, there's a theorem of Stickel-Berger where, an old theorem of Stickel-Berger where the things appear, yeah, okay, so this is not completely, when you take the trace from FQ to FP, and when you compute explicitly Gauss sums after taking the trace, you have these things appearing, so it's not completely in the air. Okay, so let me state you the main theorem. Theorem 1, so you get a phi gamma module, which you can prove that it is étal. So this M you get is the phi gamma module of an E representation of Galois QP bar over QP. Of course, I'm down to QP. And of course. Anyway, I have a phi gamma module, so, which in restriction to inertia is the tensor induction of the dual of Rho. So this is, I write it as follows. Induction from Galois QP bar over F to Galois QP bar over QP, but here I put a tensor product of Rho dual, and of course restricted to inertia. So, yeah, so this is, I insist, the tensor induction, not the tensor, the induction, the tensor induction and not the induction, because it has dimension a power of 2, so which is dimension of a tensor induction. And let me just recall, in case you don't know what a tensor induction is, so you just take the usual definition of induction, the direct sum of Gi applied to Rho dual for Gi a set of representatives of the coset, the quotient of this group by this subgroup. And instead of taking the direct sum, you take the tensor product of these things. And you can have an action of the full group on this by permutation. So this is, yeah. Okay, so this is one thing. Yeah, so the dimension is 2 to the f.
This is true for any one of these pies that you had?
Yeah, yeah. Well, from this naive recipe, yes. I don't really use much more than a little bit of the action of pi. So yeah. But this is not, this is a kind of a, okay. But what I want to do now is, so you see, you don't have a tensor induction, you have a tensor induction in restriction to inertia. So what I want to do now is to compute exactly what you have and find out the conditions so that you find out exactly the tensor induction. And this will give you conditions on my all these choices, a few conditions of all these choices I have, and
you get the tensor induction on the whole group?
yeah, I don't want just, I want to get rid of restriction to inertia. I want to start from a pi, which exactly gives me this by this recipe. And this will give me conditions on some of the choices I have, and a bit mysterious conditions. But this is a way to refine my set of pi. So that by this recipe, I get exactly the tensor induction. Let me just mention to you that if you're working with cohomology of Hilbert modular varieties, this tensor induction on the Galois side appears on this cohomology, together with the representation of the GL2 of the Adel of your totally real field. On the Galois side, it's a tensor induction. Okay, so for one can select some pi for which one recovers exactly the tensor induction and not just its restriction to inertia. So I want to explain this a bit, and so I need to introduce a little bit of combinatorics. But in this setting, there's a lot of combinatorics in all these computations. I mean, for the moment, I don't see how to avoid. Personally, I like that. Computing, find it fun, but maybe some people don't. Anyway, so now I start by a little bit of combinatorics. Okay, so one can identify non-canonically the set of embeddings of f p to the f inside E with the finite set 0f minus 1 just by choosing one embedding and composing with powers of Frobenius. Okay, by iota composed with phi minus I, which is the way it maps to I, where iota is a fixed embedding. So this is depends on the choice, but ultimately nothing really depends on this choice, what I'm going to do. So it's convenient to do this. I like doing this. I identify the embeddings with the set 0, f minus 1, like this, non-canonically. And I define P to be the subsets of this set, finite set. Okay, so cardinality of P is 2 to the f. And I'm going to define two permutations on P, on the set of subsets, 0 f minus 1, as follows. So define two permutations delta reducible and delta irreducible on P by the following formula, which this is easy. Delta reducible of a certain subset J is, by definition, those element J such that J plus 1 belongs to J. And you have to be careful that if you reach 0, you have to cycle. Okay, this is so this is a shift. This is a shift one step on the left. Somehow. Okay, and I define delta irreducible of J to be a slightly modification of this. It's delta reducible of J union f minus 1 if f minus 1 doesn't belong to delta reducible of J, and it is delta reducible of J minus f minus 1 if f minus 1 belongs to delta reducible of J. So this is the same shift on the left, except that I take the negative on f minus 1. If after my shift f minus 1 is in my set, I forget about it, and if it isn't, I add it. Okay, it's again a permutation on the subsets of P. And so this permutation, one can decompose them into cycles. Okay, decompose these permutations into cycles. So C1, C2, and so on, Cn reducible, C1, C2, Cn irreducible for n reducible and n irreducible that you can compute, of course, but which are integers, which are what they are. You can compute explicitly. Okay, so let me, I will in the sequel denote by di. It will be the length of a cycle, the cycle Ci. Okay, so I consider this shift of one step on the left on the subset of 0 f minus 1, and I decompose this permutation into cycles. And I take a modification of this permutation, and I do the same. Okay, completely elementary. And now, if you compute this tensor induction, then you find the following. This is an easy computation, which is purely so far on the Galois side. This is an easy exercise. So let me denote that delta to be delta red if rho is reducible, semi-simple, and delta irreducible if rho is irreducible, and likewise n is n red or n irreducible in both cases. Then you can, this is an exercise that the tensor induction of rho dual, you can write it as a direct summand from I equals 1 to n, the number of cycles, Vi, where Vi is usual induction from Galois Qp bar over Qp to the Di to Galois Qp bar over Qp over certain character Ki, where this guy is the unique and ramified extension of Qp of degree Di. So this is the sum of all the cycles, and this is a ramified extension of degree Di, which is the length of the cycle. So when you compute, this is easy combinatorics, this is what you find. You find something like this when you compute the tensor induction. I mean, even if rho is irreducible, this is of course far from being irreducible. You have a direct summand like this. So this is a ramified extension of Qp of degree Di, which is Ci. Okay.
You said chi was a...
Chi are certain characters that I'm not going to, I don't need, well, you can compute them, of course, but I don't need, they depend on rho, I don't need to know in this talk what they are.
By character, you mean one-dimensional?
Yeah, one-dimensional, yeah, okay. One-dimensional character of this Galois group. One-dimensional. So this, in particular, this is Di dimensional. Okay. So now let me go back to the GL. So this is purely on the Galois side. Now let me go back on GL2. And when you want to, well, okay, let me go back on GL2 now. So I have my rho, which is semi-simple and which is also sufficiently generic, otherwise all this combinatorics collapses. And then it turns out, so this is not due to me, this I guess is an observation of Fred and other people, that you can naturally identify this D of rho with P. So not quite canonically, but again, I mean, if you unravel everything, nothing ultimately depends on any choice. Let me just give you one example. In the case, remember in the split case for QP, you had two weights, sim R0 and sim P minus 3 minus R0 tensor twist. This would correspond to the empty set, and this corresponds to the whole set. I have just one element here, so.
I'm still a little bit confused by this. So what happens when f equals qp?
Well, when f equals qp, you just have one. Okay, this is just v. You just have one side. No. When f equals okay. When f equals qp depends on whether it is split or irreducible. It depends on the number of cycles. So if it is split, you have two cycles. So you have your two characters. And when it is irreducible, you have your irreducible representation of dimension 2, which is an induction. Indeed, if it is irreducible, it is an induction from a quadratic and ramified.
Right.
It's yeah, omega 2
I see.
is a character of a quadratic.
I see.
Okay, so so you can identify these weights with P. And the permutation we had previously, which I denoted delta on D of rho, coming from this S of sigma business, turns out to be exactly the permutation delta in whether you have to distinguish irreducible or reducible that I just defined on P. Here's delta on P justified. So of course this requires a proof, but this is delta on P justified. Okay, so this is a shift one step on the left in the split case and slightly modification of this in the irreducible case in terms of subsets of 0, 1, f minus 1. Okay? And so, sorry?
This delta was the thing that came up in this S exponent business.
Yeah, this, and so in particular, if you take sigma I in Ci, so now I can this Ci is a cycle of delta on P, but I also see it as a cycle on D of rho. If I take sigma I in Ci, then S to the Di is by definition is a map from sigma I I1 to sigma I I1. Since I just, this is the length of the cycle, so I apply my permutation Di, so I go back on my feet. So in the end, this is, and you can check this is an isomorphism, because S is an isomorphism. And since this is one-dimensional, this implies this is multiplication by some xi in E cross, okay, because this is one-dimensional. Okay, so I have all these xi which come out. And sorry, I need a little bit of, I'm afraid I'll be 5 minutes late again, sorry. I want to give you the full computation of this M and compare it with the phi gamma with the full tensor induction so that you see what the condition comes out. And this makes use of these xi and other stuff. Okay. Xi only depends, of course, on Ci, not on which sigma I you've chosen in Ci. Define it. And finally, I need another piece of notation. If Gi is in P, the subset of 0, f minus 1, and if it corresponds to sigma I by this notation here, then I will define Hi to be by definition the cardinality of Ji union delta of Ji minus Ji intersected with delta of Ji. Okay, this is a definition. I take the union of Ji and its shift on the left, and I.
Oh, sorry. This isomorphism between the
Yes.
steroids and P. So this is something natural, or what?
No, not quite. But whatever choice you make is not important for what you do after. I don't want to come into this. I mean, not quite, of course. It's not.
Okay,
I
but
mean, it
it's not
depends on.
arbitrary either.
Yeah, no, it's not arbitrary, of course. No, it's not arbitrary either. But I didn't tell you what this was, which is maybe a mistake. But this is I told you the example for QP, naively. Okay, so I need a final piece of notation, and then I state the last theorem, and then I'll be finished. So then I start from my row, and I can assume the following. I can always, up to twist, write row as follows. So if it is split, it is the power of the fundamental character of, say, of level f, omega f, which I write, I can always write like this, from omega f to the I equals 0 to f minus 1 of ri plus 1 p to the I. And there are unramified characters, 0, unramified of alpha. This is up to twist. This is for you, up to twist. You can always assume this. Where the ri are between 0 and p minus 1, and alpha is in E cross, and it depends on rho. Okay, and this is the thing which sends the arithmetic Frobenius to alpha, and to alpha minus 1 here. And if rho is irreducible, then if I restrict it to inertia, this is the power of omega 2f. Sigma ri plus 1 pi from I equals 0 to f minus 1. I can always write it as follows, up to twist. I plus 1 p to the I, but now I take the conjugate, p to the f, in front of it. Okay, or less up to twist, for some Ri, which are again between 0 and p minus 1. And omega f and omega 2f are Serre's fundamental character of level f and 2f, respectively. And so the full computation of this phi gamma module by the previous recipe with all these inputs is the following. So theorem 2, well, it's kind of a 1 bis anyway. M is the phi gamma module of the direct sum from I equals 1 to n of these vi, which are still on the blackboard, but they are twisted by unramified characters, alpha I minus 1, where alpha I, where you have the following formulas. Okay, so the formulas you find, for which I have no theoretical explanation, are the following. So I write it as I found them. DIHI over 2f times sigma of the Ri from I equals 0 to f minus 1 times alpha to f minus 2 gi di over f. So these, I have no, I mean, this is kind of strange formula times xi minus 1 if rho is split. And otherwise you find a sign, just a sign, but it is a certain sign, minus 1 di over 2 plus dihi over 2f times 1 plus sigma of Ri for I equals 0 to f minus 1 times xi minus 1 if rho is irreducible. So, okay, so when you do the full computation, this is what you find, these strange formulas. So you can check that this is always an integer, in case you wonder. Also, this is always an integer. So here this is just a sign, plus or minus 1. And here this is a sign, but you have a power of this alpha, which is related to these unramified characters, which have to come in the case of rho split. And this is only alpha I to the di, but remember that vi is an induction from qpdi to qp of a certain character. So when I twist by unramified of alpha I minus 1, I can put it inside the induction, and I only need to know what is alpha I to the di. This is why I have this. Okay, and so you see that you find the strange conditions, which are only clear for QP. I mean, outside of QP, I have no cannot tell you what any kind of conceptual explanation of this. That if you want one natural condition, set of conditions to have exactly the so corollary, M is phi gamma of this exactly the tensor induction of rho dual if we have for any I the following formula. So xi, this xi, which is which you get on the GL2 side, is well, you just take this to be 1 and this to be 1, so that you don't have any twist, as it was in the tensor induction. So this is -1 di hi over 2f sigma of ri alpha. Yeah, the same thing is here if rho is split, and otherwise -1 di over 2 plus di hi over 2f 1 plus sigma of ri if rho is irreducible for any I. Okay, and so these are the conditions you can now put. So remember to build my pi, I had this representation is the d naught of rho, which was a representation of k, and then I had a representation d naught of rho I1, which was a representation of n. Meaning basically here what I had was an action of 0p, 0, 1p, 0. And I can always manage to choose such an action of n so that I have these specific values of xi. And so this is what I do. I only choose those, I make this choice. And if I make this choice, I get a subset, which for QP now is exactly the correspondence. So I mean for QP you get a condition here, which is exactly what gives you your two principal series, which is not very surprising, but okay. So this enables you, so let me finish by, can refine by choosing action of 0, 1, p0, so that these xi, so that xi have these values, the values of the corollary. But unfortunately, this is still remain a lot to be done. A lot of other values from the to define an action of 0, p0, and again by my student who there's again some other choices. So we're very far, very very far from a big refinement. So this is just okay. But I mean, what is this is just a sign. So if this is really correct refinement, this means that if you modify for one I a -1 into 1, this won't be any more related to the Galois representation. So this is something which upsets me. Because of course from the GL2 side, they're very much similar. You see, so yeah, and the question remains, can one refine again? Unless I don't know. I don't know any means to do that.